Okay, so let's talk about another application of two-dimensional motion. Earlier we talked about motion in one dimension, that means a straight line. Then we talk about projectiles, two-dimensional motion. In projectiles you have objects moving under gravity. So while moving forward, it could be they're going up against the gravity and slowing down and coming back, accelerating due to the gravity. So going forward plus up or down. So that's two-dimensional motion. We're going to talk about a third type of 2D motion, circular motion. So an object is moving on a plane, on on a surface, like imagine like something, a tennis ball rolling on your tabletop, but not in a straight line, but it curves to a side. So that is two-dimensional motion, right? It has x and y, both velocities. So the special case we're going to discuss is things that are moving in circles. So in simple terms we call it circular motion. For an example, think about something like this. Let's say we have a tennis ball attached to a string, and you're gonna spin it around your head. So here you are standing here, and this hand you're gonna spin it around your head in a horizontal circle, right? So it's spinning like this, it's going in a circle like this. So this is a simple example of circular motion. So in this case, the string attached to the ball, the string that you are holding here in your hand, this is what maintains the circular path, right? We will learn this later in details in the next chapter, that you need to apply a constant force. There has to be a force all the time in order to keep something moving in a circle. Think about Newton's first law. If there is no force, objects tend to go in straight lines. So that means if you want to change it from a straight line, if you want to change the direction, you have to apply a force. So in this case, the string is applying force, and you have to do it constantly all the time. So you are changing the direction all the time. If something is moving in a circle, means it's changing its direction. The velocity is changing. It could be the same speed, but the direction is changing. Means you are applying force, you are accelerating this object all the time. Velocity is changing. Another example you can think of is planetary motion. For example, here's the sun, and here's a planet, let's say Earth, moving around the sun. It goes in an orbit like this. It's an elliptical orbit. It's not exactly a circular, not exactly a circle, but still it goes in a circular path. Now, what provides the force? What maintains this circle? What maintains Earth goes in a circle around the sun? It's the gravitational attraction between these two bodies, between this sun and Earth. Here there's a gravitational attraction. The sun is pulling on Earth towards itself, so that ensures Earth from escaping into a straight line like this. It always changes the direction into this circle. Later we will talk about another interesting example related to biology, the ultracentrifuge or the centrifuge machine that spins your biological samples, experimental samples into very fast circles. to separate these things, to separate the substance. So that's another good example of circular motion. We'll get to that later. Anything that rotates, could be a machine, could be a planet, it could be something like you're spinning a tennis ball around your head. Anything that rotates is an example of circular motion, and we can analyze the properties of this movement using a few simple equations. So that's what we're going to discuss. Okay, so without going further with examples, let's talk about properties of circular motion. Okay, let me go ahead and clear this. Alright, so let's start with a simple example. So let's say we have, let's think about that first example where you have this tennis ball attached to a string, and you're gonna spin it around your head. It goes in a circle like this. So I'm gonna draw it like looking at it from the top view. So if you look at it from the top, it's gonna look like this. So it's moving in a circle. I'm sorry that I don't have a perfect circle here. This is the center of the circle. This distance, we call it the radius, r, radius of the circle. Now here's the tennis ball. Now you're looking at it from the top, right? And it's going this way. This is the direction, so we call it, what do you call it? Counterclockwise, right? CCW. You're going counterclockwise. So at this point, the velocity is pointing straight up. Sometime later, at this point, now it's here, the velocity is pointing in this direction. We can't say it's the same velocity because the direction has changed. Let's assume that you are going at a constant speed. There is no change in the speed. The magnitude remains the same. If it is 10 meters per second, it's always 10 meters per second. Right? Here, V1, it's 10 meters per second. V2, also 10 meters per second. So let's assume that the magnitude does not change, but the direction changes. So when now velocity is a vector, right? Velocity is a vector. It has a magnitude and it has a direction. If at least one of these things are changing, we say that velocity is changing, means there's an acceleration. Delta V, velocity change, changing, change. Additionally, velocity, if the velocity is changing, it leads to acceleration. So there is an acceleration. We don't see a speed change, we only see a directional change. Still, it is considered as an acceleration, and this particular acceleration, it has a special name. We call it centripetal acceleration. Okay? If an object goes in a circular path, as long as it's not a straight line, it doesn't need to be a perfect circle. As long as it's changing the direction, it could be a portion of a circle, it could be an elliptical path, it could be a parabolic path. It doesn't need to be a perfect circle. As long as the direction is changing, we say that there is an acceleration, and we call it a centripetal acceleration, and we also assign a direction for this centripetal acceleration. The direction of this acceleration is towards the center of the circle. So if I redraw this diagram, here's this. That's not a good circle. Let me alright, let me try again. Here's the center. Here's the circle. Here's the object. Right now it goes in this direction. Here's the velocity v. This is the radius. Centripetal acceleration AC. Sometimes we just write it as A, but it's better to write it as AC, acceleration centripetal. We mark the direction towards the center. So this is very important that you remember this. Centripetal acceleration AC is towards the center of the circle. Sometimes we call it center seeking acceleration. Okay, so when something goes in a circle, even though the speed remains the same, there is still there is an acceleration. We call it centripetal acceleration. We label it as AC. The direction is given as towards the center. Centripetal acceleration is towards the center of the circle. So these are a couple of important things that you should remember. Now, what's the magnitude? If there is an acceleration, it should have a direction plus it should have a magnitude. How do you find the magnitude? Now here the velocity, the number, the magnitude of the velocity does not change, right? It's v here, and the next instant it's like this, it's like this. The only thing is direction changing. Now using some calculus, we will discuss that sometime later how to prove this, but this velocity change, if you go from this velocity 1 to velocity 2, it was originally pointing, try to draw a straight line here. It was, hold on, let me erase all this. Okay, let me try again. Let's say it was going this way, now it's pointing this way. So originally it was like this, v1, now it's pointing this way, v2. The change in direction occurred in this direction, right? The velocity change in this direction, downward direction, delta v. At any given point, the velocity is changing. Now in this case, where is the center? So this is where the center of the circle was. So in an accurate diagram we can show that. So if I make it a little shorter, in an accurate diagram we can show that it's pointing towards the center. This change is pointing towards the center. Because my distances are not that accurate, it looked like this one, so let's erase that. The change is pointing towards the center. The magnitude is given as AC equals v squared, velocity squared, divided by radius. So this is an important equation. This is how you find the centripetal acceleration. Okay.